Good morning, everyone. Welcome back to Mobile Era, the second day. It's great to see so many faces back. It's great to have you all here, and I hope you're looking forward to a fun day of talks. Without further ado, our first speaker is Colin, and he'll be presenting cryptocurrency, building a wallet for your on your phone. Please help me in welcoming him to the stage.
Cryptocurrency. It's a very broad church that has attracted many different types of people. There are the investors who are interested in day trading, interested in buying a cryptocurrency, seeing where it goes and hoping that they can turn a profit. And some of them that are interested in long-term investment who just buy cryptocurrency, keep it, and hope that eventually it will be turned into a big profit. There are the crypto anarchists. These are the people who are very interested in privacy, security. They like the idea of being their own bank, of there being no middleman, of being in control. And it's the technologists, the people who just think it's a cool piece of technology and have no greater interest than the fact that it's just a cool idea, something fun to work on, and is interesting in itself. And that's what we're going to talk about today, the technology side of things, because cryptocurrency is or does have some unique properties that make it quite interesting to talk about. So that's why we're going to talk about building a wallet on your phone. But just as a show of hands, who here has or has owned or once had and has now lost the private key to some cryptocurrency? Okay. And how many of you are confident in that you know how cryptocurrency works? Okay. So for you people, hopefully you learned something new. Apologies if you don't. We're going to talk about why cryptocurrency, why do anything with it, what's the point in doing anything with cryptocurrency. Then we're going to talk about how do we make a wallet on the phone. I'm going to get into the subject of what this all means, the bigger picture. A word of warning, in some people's minds, Bitcoin and cryptocurrency are the same thing. Bitcoin was the first cryptocurrency. There are many, many others now. Some of them are similar to Bitcoin, some of them are very different. This talk is somewhat crypto-generic, but some of the advice actually won't apply to all cryptocurrencies. I have most experience with Ethereum, which is Bitcoin similar, but it's different in some ways that we'll get into. So when I talk about cryptocurrency, I'm not talking about Bitcoin, and I'm not actually talking about any cryptocurrency in general, but I have most experience with Ethereum, so it's quite likely that it's got an Ethereum bent. Why make a wallet? Well, wallets can be created instantly, and it doesn't need any user input. So you can just create a wallet without any password, any username, without any sign-up. You can just create one out of nothing. And a wallet can be used for identification. And we're used to many different forms of identification. You know, every day we use passwords. In Norway, we use BankID to identify ourselves with the bank and other places. We use SMS round trip, using our phone as identification. Sometimes we use a passport. The bank card sometimes has a picture on it and can be used. We're used to many different forms of identification. And the wallet is really just another way of identifying you. If a wallet is created correctly, then it's unique to you, and you can use it to identify yourself. So you can instantly create a wallet without sign up, and then use that to identify a user. So you could just create a wallet on a phone, and then create a traditional service, which you have to sign up for, but just use the wallet as the identification. And as the name suggests, it's also a balance store. So you can put money in, and you can take money out. And Coinbase was one of the first players in this environment. They saw the potential of cryptocurrency, and they saw that this was a great opportunity to make a big change in the world. They saw that with financial freedom, that it improved people's lives. And so they wanted to make the killer app to make getting into the cryptocurrency environment easy and not too technical. So they created Coinbase, a service where you can buy and sell cryptocurrency, and then they eventually, on their master plan to make cryptocurrency as big as it can be, they made GDEX, a trading platform. And they recently approached us, back in Beck, and together we've created a product called Toshi. This again is lowering the barrier of entry for cryptocurrencies. So Toshi is, in essence, a chat app. It's a way to send encrypted chat between users. But we can also allow people to send money between each other, that any person in the world can send money between themselves. And we can do that and launch in every country in the world because we don't have to integrate with the banking systems. We can use cryptocurrency to allow this to happen. Toshi does some more stuff. It's also a platform where you can build chatbots and apps and decentralized apps, but I'm not going to talk about Toshi today. I'm going to talk about cryptocurrency. So that's a little bit about the why you can do this. Now I'm going to talk about how you can do this. It's a little bit technical, but it's worth exploring. So a wallet is just a private public keeper. It's nothing more fancy than that. So all you need is 256 bits of random data, and then you convert it to hex. It's extremely important that this data is random, or as random as you can get. Because if the data isn't random, what you'll end up doing is you'll end up generating the same wallet for different people, and they'll end up being able to access each other's funds. There are many horror stories about wallet creation software that isn't using true sources of randomness that I can talk about. But you'll have to find me later. So these are all potential wallets. These are all 256 bits of random data converted to 64 characters of hex. These might genuinely be someone's wallet. I don't know. I just generated them randomly. I haven't checked. But the point is that any of these can be wallets. If I remember correctly, there's 2 to the power of 160 possible wallets in the world, which is, I think, more wallets than there are atoms in the known universe. So if you have a true source of randomness, then it's unlikely that you're going to get a wallet collision. So we take one of these private keys. I just picked one randomly. And then it's going to go through this scary-looking algorithm, which is called an elliptical curve digital signature algorithm, ECDSA. All you really need to know about ECDSA is that the private key is going to go into this algorithm, and a public key is going to come out. What's important about ECDSA is it's a one-way function, which means you can put the private key in and get a public key out. Every single time you put the same private key in, you'll get the same public key out. But you cannot put the public key in and get the private key out. It's a one-way function. I'm sure many of you are familiar with what a one-way function is. But just to hit this home, I'm going to give you some examples. Say you are calculating the product of these 2 primes to end up with that number on the right. It's very trivial, at least for a computer, to multiply these 2 numbers together and end up with the result on the right. But if you only have the result of the equation, it's extremely difficult, or more difficult, to figure out which 2 numbers combine to make that number. That is one-way function. Very easy one way, very difficult the other way. If you want a more visual explanation, mixing these two colors to make a third color is very trivial to do. But if you only have the result, it's difficult to find out which two colors were combined to make that third color. Very easy one way, difficult the other way. The case of ECDSA can be explained with this metaphor. You and your friend are standing in a room that is a perfect cube. And from the floor to the ceiling on one side of the room is a curve. And your friend hands you a ball and a ping pong bat. And what you're going to do, you and your friend, is you're going to agree on where you stand in the room and where you're going to hit the ball from. And then your friend is going to leave. And you hit the ball as hard as you want. And it bounces around the room until it comes to rest. And then your friend comes back. And your friend knows the shape of the room. They know where the curve is. They know the starting point of the ball. And they know the ending point of the ball. But even with all that information, it's extremely difficult for them to figure out exactly how hard you hit the ball. And in this metaphor, how hard you hit the ball is your private key, and where the ball ends up is your public key. So the private key has gone through this ECDSA algorithm, and out of the other end comes a public key. And the public key is hashed, some data is removed, and you end up with a wallet address. And that's what you see on the right there. And this wallet, this address is unique to the wallet. And by having ownership or knowledge of the private key, you can generate this wallet over and over again. It's deterministic. And by having the private key, it's almost proof that you own this wallet address. And this is what I talked about earlier about identification. This wallet can now be used to identify you. And because ECDSA is a one-way function and it's hard to go the other way, this address is public knowledge. You can put it anywhere. You can put it in a QR code. You can email it to your friends. You can put it on Facebook. You can tattoo it on your skin. You can do whatever you want. It's completely fine to have this in the public domain. And with this address, people can send you cryptocurrency. They can send money to this address, and it will end up in your wallet. But I said that the private key, which can just be created out of random data and identifies you and allows you to create a wallet, is how you prove ownership of the wallet. But then we get into a UX problem. This private key, so the benefits of a wallet are great, but it comes with an extremely important downside, which is your wallet is only as secure as the security of your private key. And so if your private key leaks, your wallet is leaked, and your funds are as good as gone. So how do we secure the private key? So in Toshi, what we do is we keep the private key on the device. We don't upload it to our server. And that means if our server is hacked, our users' funds are still safe. But how do you tell users the importance of a private key on their phone? Because we live in a world where people lose their phones, and I used to be able to restore from backup or click forgot password, and that everything will just work out. But this private key, which came from randomness, it exists on their device, and if it's gone, and it's hard to tell people that once it's gone, there's nothing we can do. We can't restore your wallet. So there are sort of solutions here. You can tell people to back it up, but what's the average user meant to do in that situation? If they upload it to a server, that's not any more secure than if we'd uploaded it to our own server, necessarily. We can tell people to write it down, but then where are they going to write it down? Where are they going to keep it safe? So this is a difficult problem that needs solving so that it's user-friendly. Okay. As nice as it sounds, a wallet is pretty useless if you can't take money out of it. If you can't take money out of it, you've got a piggy bank. So it's great to be able to receive money, but most of us want to be able to spend money as well. So you have your wallet on your phone, someone's paid you some cryptocurrency, and you're standing in a pizza place, and you want to buy pizza. How do you do that? You need to create a transaction. And a transaction is basically you saying, I want to send this amount of cryptocurrency from my wallet to the wallet of the pizza place. Remember, the wallet address is just public knowledge. And so you create this transaction here where we've made up an amount, 100 cryptos. I'm going to send 100 cryptos from the wallet on my phone to the wallet of the pizza place. And then you're going to sign it with your private key. Again, the private key that just exists on your phone. And what you'll end up with is a hash called a transaction hash, also known as a signature. This is what it looks like. And there you go. Now you've got a signature on your phone. That's great. You can show it to the pizza guy, but they're not going to accept it because it just exists on your phone. It's just an algorithm that you've run. It doesn't mean anything. There hasn't been any conversion of money from your wallet to the other person's wallet. You've just run an algorithm. So somehow the money needs to get from your wallet to the pizza place's wallet. And how does that work? Well, now we have to take a diversion into what is a blockchain. The very super simplified version. And we can start explaining that by talking about what is a block. And a block, in essence, is a list of transactions. It's basically that transaction we just showed earlier of me sending money to the pizza place. I made that into a hash, a transaction hash or signature. A block just contains a list of these transactions. It's a list of people saying, I'm sending this amount from this wallet address to this wallet address. And a big list of transactions goes into the block. And there's also something called the nonce. And this is just a random number. And what's going to happen is this block, all the data inside the block, is going to go through something called a proof of work algorithm. And much like ECDSA, what happens with this proof of work algorithm is that this block goes through it, and it's going to generate a hash. And the important thing about the proof of work algorithm is that it takes some amount of effort to compute, but the resulting hash is extremely easy, extremely cheap to check if it's valid or not. What do I mean by that? Well, blockchains have something called the blocks on a blockchain have to fulfill a certain criteria. So in this example, the block is going to go through the proof of work algorithm, and it's only going to be deemed valid if it fulfills this criteria. So the hash needs to start with 30 zeros. So let's run this as an example. Say that this block went through the proof of work algorithm and generated this hash. The work to generate this hash took some effort, but the effort to check whether it's valid or not is trivial. We can quite quickly and easily see, even as humans, that this hash does not start with 30 zeros. So what do we do now? We increase the nonce until, and then we try again. And again, we can see it hasn't worked out. This hash is still not valid, so we try again. We try with 3, still not valid, 4. And again, this is very hard work to do, but it's very easy to verify. And then we end up with 5, still not valid. This is taking a long time. And then eventually you'll end up with a nonce that just so happens to fulfill the criteria. This block is now valid. When people talk about mining, this is exactly what they're doing. You're trying to find a nonce that fulfills the criteria of the blockchain. And in doing that, you find a block that is valid. But the criteria in this example was the same. In reality, the criteria actually changes based on the amount of blocks being produced over time. And it changes to be more and less difficult so that there's a constant stream of blocks being added to the blockchain. That's a simple explanation of a block. So now we can go back to the original question, what is a blockchain? Well, I lied about it being a simple explanation of a block because there's more in there. A block also contains a reference to the previous block. So once this block got hashed, it created a hash that was deemed valid. And that becomes the ID of the block. And so inside new blocks, you also contain a reference to the ID of the previous block, which means the reference to the previous block also goes through this proof of work algorithm, and then it's also stored in this block and cryptographically secure because of the proof of work algorithm. And because you're referencing the previous block, you end up with new blocks referencing the old block, which referenced the previous block, which referenced the previous block, and it goes on and on and on until you come to the first block, sometimes called the genesis block. These blockchains get pretty big. But once a new block is added, it just looks like this. They're all pointing to each other. So you've got a chain of blocks. And there you go. This is an example of what they might look like. This is an example of the IDs being rendered. And so each block is referencing the ID of the previous block. Now, you paid for your pizza and the transaction went into one of these blocks. Let's say it went into this one. And you've eaten the pizza and now you want to be a bit sneaky. You want your money back. What you can do, while you have a copy of the blockchain, you can just remove your transaction from the blockchain. And then it's like it almost never happened. You just got pizza for free. It's great. So what you do is you just pull that transaction out of that list of transactions, and then it's gone from history. But now the block has changed, and so you need to rerun the proof of work algorithm, which you do, and you find a nonce that matches. And so you've managed to change the block by removing your transaction, rerunning the proof of work algorithm, and you've changed history. And in doing so, you've changed the ID hash of the block, which is great. But now this block is no longer pointing at the previous block because its ID has changed. So now what you have to do is you have to rerun the proof of work algorithm on all the blocks that came afterwards, which takes some time, but it's completely possible. It's extremely hard work, but you can get it done, and then you can just change history whenever you want. Unfortunately, the blockchain is also distributed around the whole world, which means that if you ever want to change history, you're going to have to change it on every node that's running the blockchain in the whole world, which is obviously impossible to do. So what this proof of work algorithm and the cryptographic hashing and the referencing of previous blocks does is it essentially ensures that the data becomes immutable once it's on the blockchain. It's very difficult to change. And by distributing the blockchain to nodes around the network, it's impossible to change because you have to change it on everyone's computer at the same time. So that is a blockchain. But we're still trying to buy pizza. And now we have an understanding of the blockchain, but we still haven't really figured out how we're going to get our pizza. Well, now you've got the transaction hash. You need to push it out to that node of networks, and then eventually it will get mined onto a block and put onto the blockchain. So if you've got a wallet on your phone, you can just push it out to the node of networks, the network of nodes even. That's great, but that means you need a copy of the blockchain on your device. And that doesn't come for cheap because blockchains are big, hundreds of megabytes, possibly gigabytes. And then there's also the networking cost, speaking to all the nodes and keeping your blockchain in sync and syncing transactions between each other. So in the case of Toshi, what we do is that we have a blockchain server. It is a node on the network, and then our client is speaking to the backend server. This is a classic compromise between usability and security. Because what happens in this situation is that you're giving control over to the server, and you have to trust that the server is both pushing your transaction out to the network and telling you the truth about the state of the transactions, and also telling you the truth about the balance of your wallet. There are two important caveats here. One, the private key still only ever exists on the phone. So even though you're putting trust onto the server still doesn't have access to your wallet and can't make transactions on your behalf and take money out of your wallet. Your wallet is still safe. And because the blockchain, as you saw, is so heavily distributed, you can very easily verify independently on another service whether the blockchain state, as being reported by the server, is correct or not. So it's very easy to verify whether this server is lying or not. Just a little bit about how you can do it. And if you want more technical details, you can find me afterwards. I might be able to answer some of your more technical questions. But we can go back to why we do this. Because in the case of Ethereum in particular, there's another important reason why you might want to build a wallet on your phone. And that's the ability to interact with smart contracts. And the simple version of smart contracts is, this is just code that is deployed to the blockchain. It's some logic that you put into a block, and then the block gets put on the blockchain. So, I said this is what a block looks like. Kind of lied again, because it can also contain a smart contract. This is just some code, some logic. It's written in Ethereum, it's written in a language called Solidity, but it can be translated into different languages. It's just some logic. Anyone can write it. You can put it up. It doesn't even have to compile. Just some code. It just exists. And so this is what a blockchain, this is a representation of a blockchain with a smart contract in one of the blocks. So this is code on the blockchain. And when we talked earlier about sending a transaction to the blockchain, you can actually just send a transaction directly to the smart contract. And in doing so, what you're doing is you're causing that code to be executed. So the code that exists on the blockchain can be executed from the wallet on your phone. And that code will be run, and the output of the execution, the state, after it's been run, will then be added as a transaction on the blockchain. So what that means is that you can run some code on the blockchain, and the result goes into the blockchain, which, as we discussed earlier, is immutable. So you can run, execute, get a result, and know that it can't be changed. Now that was a bit abstract. So what does all that really mean? I can give you an example. Say that you are a researcher running an experiment, and what you've created is some hardware that has a wallet on it, and it's going to detect the weather at that location where the hardware is, and you send hardware out all over the world. It's a very simple app, just detects the weather, and then it's going to record it. You could write a smart contract, deploy it onto the blockchain, and what the smart contract could say is that when this phone records the weather, just record it in the blockchain. Why would you want to do that? Well, it basically means that the data that's recorded from that phone after being executed by the smart contract goes into the blockchain, which means that data is immutable. It can't be changed. And it's also time-stamped. These two things are kind of important because if you're running a research project, you want to ensure that the research, the raw data, can't be tweaked to match the results that a vested interest might want to end up with. You can very easily verify, or the raw data is secure. So if someone is claiming that if someone is tweaking the raw data to match the vested interest, you can quickly verify the claims. And you can do that because the blockchain is open. It's distributed around the world. So the data is open. The data is open to everyone. Anyone who has a copy of the blockchain has a copy of the data, which has some side effects because you might be running an experiment about climate change, but the data just exists there. So anyone else later on who wants to do a different experiment and also needs access to that data can just get it by getting a copy of the blockchain. We will take one more example. Say your job is driving around your neighborhood, picking up parcels for delivery. But you don't actually deliver them to the final destination yourself. You drive around, collect them all, and then at the end of the day, you deliver them to a delivery company that's going to have the job of getting them to their final destination. But you don't work for the delivery company. You're just freelance. This is just a job that you're just doing it as a contractor. And so the responsibility for the parcels is yours up until you give them to the delivery company. But if the delivery company just happens to lose a parcel, then how do you prove to the original customer that it wasn't you that lost it, it was the delivery company? Like the delivery company, you could sign a receipt or something, but if push came to shove, I don't think it would maybe be the best evidence because the delivery company could still deny that the receipt was ever signed by them. So instead, you could deploy a smart contract to the blockchain. And what this smart contract will do is that it will allow, at the point of handing over the parcels from yourself to the delivery company, you both to sign a receipt on the blockchain saying that you handed over 10 parcels. So when you arrive, you hand over your 10 parcels to the delivery company, and then you send a transaction to the smart contract saying, I just sent over 10 parcels. And then the delivery company does the same, saying, I just received 10 parcels. And you both have a copy of the blockchain, so you can easily verify that both parties have done what they said they should do before you leave. And you get all the same benefits as you had before. So that receipt will go into the blockchain and can't be changed. So the delivery company can't trick later by changing the data or the receipt to say something different. It's time-stamped and it's open to everyone. So anyone can verify that the receipt exists and that it actually happened. But it also gives another benefit, which is trust. The private key of the delivery person, of the driver, shows that the transaction was signed by them and only them, and the same for the delivery company. No one else could have signed this transaction saying that they sent or received 10 parcels. Both of them can verify that the receipt went into the blockchain before they leave. So both don't need to trust each other, they just need to trust the blockchain. And this gives you a notion of decentralized trust. The source code for the smart contract is also open. Anyone can verify that it's doing what it says it's going to do. And no one needs to trust anyone. This just exists on the blockchain. No one owns it. No one can change the smart contract after the fact. It just is a thing that exists that you can interact with. And there's no need for any of these parties to trust each other. They just need to verify that what they said was going to happen does happen and what's in the blockchain. They can rest. They can be secure that the data won't change. So in summary, what do you get with a wallet? You get a notion of identity, being able to identify yourself securely, because the private key is a form of identification. You get a balance store, the ability to send and receive monetary transactions. And then you get the ability to interact with smart contracts. And that notion of smart contracts allows you to use blockchain as a service. In our previous example, there was no other backend component being run by anyone. The blockchain was the backend. Blockchain as a service. And through that, you get some unique properties. You get openness by default. You get immutable data and all the benefits that come with that. And you get this notion of decentralized trust. That's all I got. Thank you for listening.